screen. All right. So we talked about the limit definition of the derivative, right? Pretty good, felt reasonable. We talked about how this was really just finding the slope of a line, all of that good stuff like that. What I want to do before we get too far is I want to use this so you can get a slightly better visual. So if I ask you to find the slope of the tangent line to this function, and this is a really gross function, I have no clue. I suppose you can figure it out from there. But this is a quadratic, and we are looking at apparently where x is 2.914. Sure, that sounds cool. Yeah, I agree. I don't know why we would look there either. But we are. All right? And the x value is 1.575. You can kind of see that right there. If I were to draw a tangent line through that point P, we would have this point, this line exactly, and we would have a slope of 0.450. The problem is we really don't know how to find that. So what we would have to do is we'd have to come up with the second point, x plus h. And from that x plus h, we would make another point. Let's call that point Q. That all makes pretty good sense so far? Yeah. And of course, if I connect point P and Q, we would have a secant line. All right? Now, as you can see, point PQ, because h is a fairly large number here, the slope of line PQ is nowhere close to the slope of my tangent line. But how do we correct this problem? Remember, if I don't want a secant line, I want to try to make it look like a tangent. So what can I do with Q? Move it down. I can move it down along the x's and make h smaller. How small can I make h? We can make h approach. And as we get closer, of course, the secant line becomes the line. And when we get h to go to 0, remember, it doesn't become 0, but it moves towards 0. As we get really close, you watch that tangent line become 4.5. That is why, of course, we let h equal 0, we get a perfect match. And that's how we get that definition of a derivative, just so now you got a cool picture to go with it. Jake, you look like you almost had a question and then it turned into a yawn. It's okay. I hate my yawn questions. Of course, now you're officially forever being asked in my video if you had a question that turned into a yawn.
Wait, is this going to apology?
Yeah.
Oh no.
All right.
Mr. Ackerman.
So, we're trying to find the slope of the line, and if I want to find the derivative at 3 points, right now, the only way you know how to do this, the only way you can do this right now is using this limit definition, this idea of limit h approaches 0. Definition of the derivative. It says f of x plus h. When we say f of x plus h, what am I actually talking about? How would I use f of x plus h if I've got an equation like that? Yeah, plug in x plus h for all my x's. So this becomes, I'm going to put a bracket so I know that I'm doing this all together. This is x plus h squared minus 3 times x plus h plus 1. And I'm going to subtract from that now, I want to try to get through this as quickly as possible. So here you go. Ready? I'm going to do a whole bunch of algebra. And after I've done a whole bunch of algebra, I'm going to get this statement. Hold on. After a lot of work, we're going to get the limit as h approaches 0 of 2xh. Yeah, can I just do that? 3h plus h squared all over h. Believe it or not, there was rhyme and reason to how I got that. You just don't know it yet. and as I do that, I would get what? So we finish this off. All of these h's factor out. We get 2x minus 3 plus h. And if h goes to 0, that plus h is gone. We get... Now, 2x minus 3, we have a special notation for that. There are two ways I can write a derivative. I can use what's called the Newton notation, f prime of x. It tells me that I'm looking at the first derivative of f. Now, first derivative only means I've done the derivative to the equation one time. If I wanted to do the second derivative, not only would I have done this, but then I would have done the whole thing again to that equation to get a second derivative. And we would do that f double prime. We also have this notation, dy dx. That's called the Leibniz notation. And we can do multiple versions of that as well, although that gets weird. You'll see it eventually. I'm not going to talk about it too much right now. In fact, there's a whole list of ways I could actually tell you. Y prime is technically correct. I don't use this. Okay, this one right here, I don't use. I don't like that notation. It tends to get a little bit weird. The other thing that I start thinking is when people get sloppy with it, they put y prime and it looks like y to the first. And then I try to figure out why you put y to the first. Then other people decide to try to figure out why you put y to the first. If I ever have a y, I'm going to write it this way. These would be my two main methods. This tells me to take the derivative of f of x. One more thing about this. This gives a general solution. What do I mean by that? I mean that when you plug in and you actually do that problem, you will get some sort of functional output, 2x minus 3. That equation can be used to find the slope of that tangent line at any point along the curve. So in this problem right here, I can actually use this 2x minus 3 to find, what is that, negative 1? F prime of negative 1, f prime of 0, and f prime of 2. And by simply substituting in the x value, I can get the slope of the tangent line at any point on the curve. So when I sub in a negative 1, I get 2 times negative 1 minus 3. I get negative 5. The slope of the tangent line of x squared minus 3x plus 5, or plus 1, at x equals negative 1 is negative 5. The slope of the tangent line of f of x when x is 0 is negative 3. The slope of the tangent line of f of x at x equals 2 is exactly 1. Pretty cool. Now, that is the definition of the derivative. There's also an alternate form of the definition of the derivative. All right? This is for specific points. And I am going to skip over to a different one here. Yes, I'll do it right here. The alternate form of the definition of the derivative. I just want to show you how it works. In this problem, I may be tempted to do the alternate form of the definition of the derivative. The reason being is because I'm just trying to find the equation of a tangent line at the x value of 2. Now, when you read through the instructions, it says, write the equation of a tangent line to the graph. What do you need to write the equation of a line? You always need a slope. And then you always need a... we don't need a y-intercept. We could do it with just any generic point. right? But we will need a slope and we will need a y, at least a point, not a y-intercept necessarily. So when I look, do I have the point? Yes. That's 2, 6. That's given to us. But do I have the slope? No. We need to come up with that. Another way of finding a slope at a specific spot is to use the derivative. Remember, the derivative is the slope of the tangent line. That is going to be drilled into your heads. And if you don't believe me, ask Armando. Yes, this is something to memorize right there. Slope of the tangent line is the derivative. So to find that, we would have to find f prime of 2. Using the alternate form, it changes a little. We're going to let x turn into 2. For those of you, this is on the other page. I'm going to put it on here just so you can see what I'm using. Using the limit as x approaches. It says a, I'm going to use c. F of x minus f of c, x minus c. That's the alternate form. That should become pretty obvious because we have a point and another point, but I'm going to let the x point go to c, and when those become c's, what happens? Becomes 0 over. Okay. Limit as x approaches c? Well, f of x is what? X squared plus x, right? We're going to subtract from that f of c. In this case, c is 2. So 2 squared plus 2 all over x minus 2. That's what? X squared minus, or plus x. This is minus 6. What can I do to the numerator? X minus 2, x plus 3. And what do I have? Which is? As the x goes to 2? So the slope of my tangent line correct. All right. I have a slope, I have a point. How do I write the equation of a line? Close. Your y and your y1 were backwards, but that's what I want to do. I want to use point slope form. I want to do y minus y1, which is 6 equals the m. 5 times x minus x1, which is 2. Then what do I do? Do order of operations. Yep. Order of operation number 1, box the answer. Bingo. Kevon has that right. We do not want to do any math. We do not want to do any arithmetic because I find that with most calculus students, it's the numbers that are hard. All right. Now, we've done a couple examples of these. Knowing how to do the limit is important. Understanding that the slope of the tangent line is a limit, that the derivative is a limit where the points are going to go to the same spot is important. Knowing the derivative is the slope of the tangent line is important. How would you like to all learn how to cheat?
I do.
Ladies and gentlemen, go to the next section of the notes. Let's speed this process up a little bit. Then we can get to some more interesting problems. All right. So, derivatives. Taking derivatives with the limit takes a long time. Typically, I would set aside 2 days or so to be able to go through that section. Sadly, with the hurricane, I don't have that ability. However, we can speed this up a lot. See, whenever I got a polynomial term, some x to the nth power, be it x squared, which we've done a couple times, x to the third, x to the fourth, x to the 100th. X to the 100th gets really annoying, by the way, when you do this. Just going to say, when you do the definition of the derivative, because you'd have to multiply x plus h out 100 times. Yeah, that sounds terrible, doesn't it? Of course, we could simplify that a little bit, you see, because if it's just x to the nth power, that n becomes a multiple of the x. And then the power simply reduces by 1. You see, instead of having to do x plus h to the 7th power minus x to the 7th power all over h and all that stuff, I can just say that the f prime here is equal to 7x to the 6th. See this cubic root, that looks really gross, but you see cubic roots are cool because I can take a cubic root and I can rewrite that. I can write that x to the 1/3. It was on the summer assignment. Which means x to the 1/3 here, well that means that g prime of x is simply 1/3 x, take the 1/3, multiply it up front, and then subtract 1 from 1/3 and get negative 2/3. Now, okay, my instructions say do not leave negative exponents. Fine. 1 over 3x to the 2/3. Also says complex fractions. My argument, that's not a complex fraction, that's an exponent. See the letter C down there, y equals 1 over x squared, but I can rewrite that. I can rewrite that as x to the negative 2. You see, that's really useful now, because see, I can find the derivative of y, which I'm going to write as dy dx. Dy dx is simply take the negative 2, multiply it in front, x to the, not negative 1. Negative 3. We're reducing it by 1. It is a common mistake, so do not feel bad if you wind up doing that the first, up to the positive 3. I fixed it. Be very careful of that. That's a really common mistake. Subtracting 1 and then accidentally just bringing it close to 0. Cubic root of x to the 4th. Well, rewrite it. X to the 4/3. So, if I want to find the derivative, f prime of x, it's what? That's it. 4/3 x to the 1/3. Not too bad? That's it. That's all there is to that rule. See, and I can pretend like, okay, we can pretend like we can make that maybe a little bit harder. Hold on, I got to change page to get to the bottom stuff for some reason. If I'm not going to worry about this one up here. You can figure out these. What is f prime of x, though? Oh, we'll do it real quick. It won't take that long. All right, so if I want the slope at x equals negative 1, then really all I just want is f prime of negative 1, which is? It's negative 4. 4 times negative 1 to the 3rd. If I have x going to the 0, f prime of 0 is? If I want x to the 2nd, then I want f prime of 2, which is? So what about this question on the bottom? Find the equation of the tangent line to the graph f of x equals x squared, where x is equal to negative 2. Well, read the question. What's the question asking for?
Find the equation.
Equation of a?
Tangent line.
What do you need for a tangent line? Point and a slope. How do you find the point? Plug in x into what? To f of x. So I want the f of -2. That's what, -2 squared? How do you find the point? Or sorry, not the point, the slope. Nope. How do you find the slope? How do you find the slope of a tangent line? Do what, Edwin? Or not? Why did I call you that? Aaron? Andy. Steve? If I'm going to screw up, man, I'm just going to go the other end of the alphabet. I'm going to call you Zach now. All right, Andy, what did you say earlier? Yeah, take a derivative. What is f prime of x? So to find the slope of the tangent line, we need to substitute in the -2 into f prime. Or 2 times -2. Now you're not done yet. All right, a couple more rules to know. Derivative of a constant. C is a constant. Tell me what you know about the graph of an equation that is a constant. So like y equals 6. Slope is 0. What does derivative represent? Slope of a tangent line. So it would be the slope of a tangent line if the line we're already based off of has the slope of 0. Still be 0. I know, it's pretty awesome. If there's a constant, we didn't get a chance to really discuss this. I'll put up a video for this. But there are some properties, and one of the interesting properties that we have with limits is that if I have a constant for a limit, that constant, remember that constant doesn't really get affected by the limit itself, right? If I do the limit as x goes to 5 of 3 times x, does the 3 really change at all? No. So an interesting outcome of that is that I can actually take the 3. In this case, this would tell me to do 3 times 5, which is 15, right? In this problem, I'm telling you to do the limit as this goes to 5 is 5, and then multiply it by 3, which is? Well, guess what? If that's true for limits, and a derivative is a, then shouldn't it have the same rules? C times n x to the n minus 1. Also, sums and differences. If I have the derivative of f of x plus g of x, that is the equivalent as the derivative of f of x plus the derivative of g of x. And if that's true for addition, then that's also true of subtraction. Because all subtraction is addition multiplied by -1 on one term. With that actually gives us the ability to do a whole bunch of different types of questions. I'm going to give you all about, let's see how fast you can get through these. See how far you can get in about 2 to 3 minutes. All right. Some of these are going to require rewriting and some of them are not. All right? Oz, did you have to rewrite A? Do you have to rewrite A? What do you think, Oz? Oz. No. Does this look like it's something 2 to a x times something x to a power? Does that look like x to a power to you? It does? Okay, what is it, x to a power? Okay. Where do you see a negative? Oh, there you go. All right. So now when you take a derivative, what did you get? This isn't scary. Come on. Ignore the 2. X to the negative 1. Probably. I'm thinking you spent 2 minutes with nothing on your paper. Thinking how the heck you're going to get better at calculus if you're going to sit here and watch me do it. All right. Us, you've got D. So it better be done by the time I get to D, which may be pretty quick. Edwin, what's the answer? Reduce the power by 1.
Oh, wait, what's on negative? Oh, yeah, okay.
Common mistake, and that is a huge mistake that happens with negative 1. Negative 1 power, everybody wants to call it to the 0 power because they're going, oh, make it smaller, it goes to 0. Isn't that happy? And then we could rewrite that negative 2 over x squared. Awesome. Andy, who I didn't call 15 different names earlier in this video. B. Eight t over 5? I love it. Could call it 8/5 t. Yeah. Yeah, so if you wanted to write that 8/5 t, that is perfectly acceptable. Now, I suppose if you really wanted to call that 4 over 2.5, but I don't know why you'd want to do that. Abel, C. Everybody's now furiously working ahead.
Negative 1 x squared over x squared.
Negative 1 over x squared would be good. It's actually not over x squared, though. It would be x to the 1/2. Because if we actually took this power, let me real quick write out what this turns out to be. This becomes negative x to the negative 1/2. Remember, you're going to subtract 1 from this, which is negative 2x to the positive 1/2. Right? All right, Oz. Back to you. He's got this. Yes. Bingo. Multiplying the exponent times the front. So, yeah, you take the 2/3 times 3. Yeah. Beautiful. That's exactly what it would be. See? So, let me reverse the question that you had earlier. Are you thinking too hard about this? Probably. Oh. Trin. You get this creepy looking thing. E. Ah, you can do it. You got this. There was going, oh, he wants us to go beyond. Holy smokes, here we go. So what do you think this becomes? Well, what is this? Ignore these. What's that going to be? So the derivative of x to the third is what? X squared. What's the derivative of this one going to be? What's the derivative of that going to be? What's the derivative of that going to be? It's not negative 20, because that would be a constant. The derivative of a constant is? No, because there is no x here. Or the way you could, one of the ways I've kind of explained it before is if you've got an x to the 0 power, wouldn't that 0 come out? And 20 times 0 is 0. So the term goes to 0. The other way to think, the better way to think about that, think about the slope of a constant function, negative 20. A constant has a 0 slope, so the derivative of a tangent line is going to have a 0 slope. What I want to point out in that question, did I do anything special even though there were 4 terms there? Just did each individual term. Okay? Astrid.
So that would be 12x squared minus 10x plus 7.
What happens to the 3?
Well, you don't have the 3 for it, so you can't separate.
Well, we can take the derivative of it.
Well,
The derivative of a constant is?
Yeah.
Bingo. And that's, don't get too involved in what you're doing there. Just derivative of a constant is 0. G. That looks weird. That looks hard. We should rewrite it. Have a common denominator of x. Can I take each of my terms and take that common denominator and split it amongst all of the terms? Did I do anything weird there? Basically, I did common denominator, but I did that backwards. So instead of finding a common denominator and combining like terms, I broke them apart as if they still had a common denominator. If I write it this way, I can actually simplify this a little bit, can't I? What 5x to the 5th over x become? What's the next term? Plus. Fantastic. Kevon. Destroy it, man. You got this. Beautiful. Almost. There it is. It's like, oh, sweet. I'm awesome. Oh. Jake, I haven't picked on you. It's a great idea. You got this. G prime. What you got? Yes, you do. It's not that bad. How's it work? What should I do with that for? Yeah, bring the exponent down in front. That's negative 4 over 2, which is what? Over 2 is just 1/2. What's next? I'm still looking at you, man. What have we done the last 7 problems? Okay. You have not stopped me. What are you losing on it? Yeah, it's just power rule. Take 3, multiply it up here. Yeah, it's the same problem as you have. The only thing I dislike is you have a 3, but you also have a 3 up here, so what do I do with those 3? Yeah, that's it. Minus? See? Oh, ye of little faith. All right. What I'm going to do real fast is I'm going to write these down. You're going to have a table. You're going to blindly do this, and we're going to discuss this more tomorrow because we are about to run out of time, and I want to make sure we have enough time to do, you have all the things you need. So, this is the back of this is whatever the next page is. I will go through these in more depth. Oops. Negative cosecant squared x. That is secant x times tangent x. All right. Yeah, these are the 6 derivatives these are 6 of the 9 derivatives you will have to learn for these. If you thought that you did a lot with trigonometric functions and pre-calculus, we're going to use them quite a bit. Not as much with the identities. There's only a few identities we need to know. Let me put some stars next to ones that are going to be really important. The 3 on the left are going to be the ones that you're really going to want to find. And really out of even those 3, sine and cosine are the biggest out of the 2. Tangent, while important, we're going to find out we can actually derive that. The problem is I can't really teach you the tangent derivation until I teach you another rule. But hopefully I have enough time to go through all of this. What does the sine graph look like? It's an S and it starts at, and it goes up or down. Okay, here's how I memorize this. Sine and cosine, they flip-flop. Can't really do much with that. But here's what I want to point out. When I take the derivative of sine, notice, how does it start off? It starts off by going up, and a derivative is just the slope of the tangent line, right? So what type of slope does sine start with? Positive slope. Now think about the cosine function. Cosine function starts where? And goes? So why is the derivative of cosine negative? Because the slope is? Bingo, Ackerman. He is. All right. It's always fun when I have little random times that I go in there. So if we think about the cosine versus the sine of x function, that will help you with the signs. The other thing that's cool about this, if I take the derivative of sine of x, that leads to the cosine of x, right? If I take the derivative of cosine, I just said we go to the negative sine of x. If I take the derivative of negative sine, and we take the derivative of negative cosine,
time we have here. Calculus with attributes.
That's right.
Smash that like button.